In this example, we have a support consists of a vertical plate with the size b times t. Right? It's b wide and t thick. And the support, it supports a load of p, determines the normal stress acting at point H. Okay, the H is right here. And of course, we can also ask you to calculate the stress at point K. Okay. So first of all, if you want to calculate the stress at H, you should realize that it is subjected to combined loading because the P is not added as the centroid of the plate. Okay, it has a distance C to the right edge. But what is the distance from the loading to the centroid? Okay, so here it equals the first component due to axial loading, and the second component due to bending moment. Okay, the first component equals F over A, the second due to bending, right, MC over I. Okay, here obviously we need to determine the F and M at the beginning. Perhaps you can tell the F and M directly, but if you cannot, okay, we need to do the first step, free body diagram. Okay, to cut it free here, cut it to make the this part free, right? So we will have a normal stress and a bending moment. Okay, this is the F, this is the M. Okay, so sum Fy equals 0. From here you will get F equals P. Right, that is here 1,200 Newton. And sum M equals 0. You will get the M equals what? Equals P times C plus half T. Right? Because the C is the distance from the loading to the right edge of the cross section. Okay, you still have half thickness to the centroid. Okay, here is the centroid, right? And you have a T, half T here, plus a C. Right, so this is the arm of the P. Right, consider these numbers. Here it equals 39,000 Newton millimeter. Then the section properties. A equals just B times T. Right, the B 60, T is 15, so it's 900 square millimeter. Then the IY, when we're calculating IY, right, here is the y-axis, because this is the y-axis, and when you add this P, this cross-section will be bended about y-axis, so we're calculating IY. So how to calculate IY? It's not IX, right? On this cross-section, if we're calculating IX, it's TB cubed over 12. While if we're calculating IY, it should be BT cubed over 12. Right? So this is important. Not TB cubed over 12. The result here is 16,875 millimeter to the fourth. Okay, then we can calculate the sigma 1, that is F over A, right? F 1200 over A 900, we get 1.33 MPa. And for the second component, so we need to know the C equals half of the thickness. Right, that is 7.5 millimeter. Then the second component will be MC over I. So that is 39,000 times 7.5 over 16,875. You get 16 MPa. Okay. So this stress is its magnitude is the same at point H and point K. Just when on one of them is positive and one of them is negative, right? So what is the value? What is the sign on the side of H? At point H, sigma 2 equals what? Positive or negative 16 MPa. Will be in compression, right? Since the bending moment is in such a way, so on the point of H, it will be in compression. So this is negative 16 MPa. Right, so the stress at point H will be 1.33 minus 16. Oh. Here is a 17.33 MPa. Okay. .33 MPa. So the stress at H will be negative 16 MPa. This is in compression. Right, then how about at point K? At K, the second component is, of course, positive. Right? So the stress at point K will be 1.33 plus 17.33. That will be 18.66. This is in tension.